Okay, good. Start testing. Okay, so today we're going to talk about sort of what use is this P versus NP stuff. Now, fundamentally, I mean, if you don't understand P versus NP, then you don't really understand computer science. I mean, this is like if people say, oh, well, if you were in chemistry, nobody would say, why do I have to know? You remember, like hundreds of years ago, people tried to turn lead into gold. And you can't do that with chemical reactions because they're elements. But what if somebody said, well, why do I have to know why you can't turn lead into gold? What's the use is it to know that you can't do something? I'm interested in the stuff you can do. And you actually hear people talking about P versus NP this way. And they're like, yeah, well, I don't care. Maybe you can do clique and poly time, but if the exponent is really big, then it doesn't make a difference to me. Okay, people who say, why does it matter? Why do I have to learn why you can't turn lead into gold? They don't understand chemistry, and they don't seem to want to understand chemistry. People who say, well, why does it matter that, if we can do clique and poly time, if maybe the exponent is really big? They don't understand computer science, and they don't really want to understand computer science. If you don't understand why you can't go faster than light, and you're not curious about that, and you don't want to know, and you're only interested in the stuff you can do and you can make money from, then you're not really a physicist, right? You can find a polytime algorithm for all of them. That seems to be interesting. Anyone else? Anyone else? What? My internet is. Okay. I'm going to switch and try to connect through my phone. This means I'm going to disappear for a second. I don't know why my internet is so bad. This is really going to burn down my data, but okay. Okay, so I was saying that that people ask, one free hour. I have Kudo on my phone and Eastlink in my apartment. Tethering portable hotspot, but I never use my data anyway, so I should be fine. So now, I don't know why this. Okay, I'm going to switch over to the phone, so I may disappear for a second. Can you see me? Okay, so this is going through the phone. We hope this works. Okay, so yes, one of the reasons. So in this book, actually, if you look at the scribe notes from last year, so in this book, there's this description of, there's a cartoon, which I should have looked up earlier, of the Bandersnatch problem. Right, here it is. Oh, right, it's on page 2. That should have been easy. So what happens is they're saying, well, one of the reasons they said, one of the reasons to study this NP completeness stuff is so that you just don't keep. This is the Gary and Johnson Computers and Interactability Guide to the Theory of NP. Everyone just calls it Gary and Johnson. Nobody ever says the title. Gary, G-A-R-E-Y, Johnson with an H-N. Okay, so they say, suppose that you find a problem and you can't find an algorithm for it. Well, you don't want to be in the first figure where it says, I can't find an efficient algorithm. I guess I'm just too dumb. Right. So if for example, and then if you could do a reduction from the halting problem to your problem. So show that if you could solve your problem, then you could solve the halting problem. Then you can say, I can't find an efficient algorithm because no such algorithm exists, right? Or if you could actually unconditionally show that something is, now there are actually problems that we can show that, like the halting problem. I haven't talked about any of the other ones. There are problems that we can solve, but which you can't solve in polynomial time. So if you can say that, great. Then you're sort of off the, I mean, you're not exactly off the hook, because then your boss is still going to want you to do something. Like there are problems we have to solve, and I'm worried. Yeah, I'm seems to still be okay. There are problems we have to solve, and like people are saying, oh, like we need this, and you're like, too bad, it's impossible. And they're like, well, what can you do? You can do approximations. You can deal with deal with special cases. You can, you have heuristics. So then you fall back on not trying to find an exact algorithm. But that doesn't happen that often, that you can actually prove unconditionally that there is not a polynomial time algorithm for the problem. Like we can't prove that for SAT or clique or independent set or ham path, whatever. We can't prove that P is not equal to NP, so we can't actually, so I mean, yeah, fine. If you can prove P is not equal to NP, great. But usually what you're aiming for is this last one that says, I can't find an efficient algorithm, but neither can all of these other people. So you can now say, look, for 50, if you go out and you get a job and your boss gives you a problem, then and you can't find a solution after a week, you turn around, you see, okay, is this NP hard? You try to do a reduction. Is this NP? Okay. You try to do a reduction from some problem you know is NP complete to this problem. And if you can do that, you can say, okay, you can't, I'm unlikely to find a polytime algorithm that gives you an exact solution. People still there? Okay, so this actually, okay, good. So this actually does happen. I mean, your boss is, if they're a manager or something, they haven't done computer science, these problems, there are hundreds of problems in that book that people have actually tried to solve and which we now don't try to solve exactly because we've managed to show that they're NP complete. So for example, a few years ago, I was at the University of Helsinki, and a friend from Japan was visiting, and she wanted us to work on this problem. Given a string, can you partition it into the minimum number? Can you partition it into palindromes, palindromic substrings, such that each palindrome is unique? And she said, okay, let's work on that. I think we can do it. And two of us said, that sounds hard. So, but she kept insisting that we should work on this. So finally we said, look, okay, we 9 of us got together in a room, and for 3 hours we hacked at it, and we proved that it's NP complete. We reduced, I mean, obviously it's in NP because given a solution, yes, you can check it. Given a partition, then you can check each substring as a palindrome and that they're not equal. But we reduced circuit SAT to it, which, I mean, we got a paper out of it. It's brutal. Said like, they'll do this. So yeah, if your boss gives you a problem and you say like, okay, well, in order for you, and you go to it, and you go back and you say, well, I can find an approximation, and the boss says, what are you talking about? An approximation? I want an exact answer. You're fired. And you can say, well, look, it's you shouldn't fire me. It's maybe you do, but it's unfair if you do, because it's very unlikely anybody's going to find you an exact polytime algorithm. Okay, so that's, yes, there is some use. And then after you get into approximation algorithms, heuristics, and fixed parameter tractability, and blah, blah, blah. So yeah, there's that. To know that we can stop, and you don't have to keep wasting your time. But there are also, so there are two reasons. One, you should just understand this because it's at the core of computer science, and it's like, to understand why you can do what you do, you have to understand why you can't do what you can't do. Now, when I say can't do, I'm assuming that P is not equal to. And to understand, I need to really understand when people talk about this, what does it mean? But today, I'm going to show you two things that you can do, like positive results that you can actually do. Well, sort of positive result. One thing you can do with NP completeness, and another thing where it's not just out there affecting problems which are hard, but it's sort of, we work in P, the class of problems in which we can solve in polynomial time, right? We think about, like, those are the things that you can do in reasonable amounts of time. And we can actually, I'll show you that you can actually use results about NP completeness to prove lower bounds on problems that we can do in polynomial time. And that's kind of new and very popular in complexity theory. Okay. So I don't know if shouldn't take the full hour and a half, but we've gone on for like 15 minutes already. So, okay. So the first thing we're going to see is something called zero knowledge. Okay. This is kind of cool. It's from cryptography. And actually, I used to know the guy. He's a professor, another professor. Cook is at Toronto. This is another professor at Toronto. Toronto has a very strong complexity theory group. So this guy, Charlie Rakoff, he got the Gödel Prize for this, and then the two co-authors, Shafi Goldwasser and Silvio Macali, got the Turing Award for this, because it's this idea of something called an interactive proof. And this is, I mean, usually if somebody says prove something to me, you think, okay, it's a proof, and then you're 100% sure. This is sort of a statistical thing where I can convince you to any extent that you want, but you're only 99.99999% sure that I'm actually not lying. Okay, so I hope you're going to understand this by the time we get through. So what is zero? Why is it called zero? Now, interactive proofs are lots of other stuff. Zero knowledge, technically a zero knowledge proof of knowledge is when I want to convince you that I know something, but I don't want to tell you what I know. Now, this is, I mean, the absolute worst outcome of a course is when you think you don't know what the course is about, and you think the professor doesn't either. The best is when you come out of the course and you understand everything and you believe the professor does too. In the middle is when you believe the professor knows what he's talking about, but you have no idea what's going on. So that's sort of like, so what I'm not supposed to be doing as a teacher is zero knowledge proof of knowledge. I'm not supposed to be trying to convince you that I know what I'm doing, but I'm not going to teach you. However, just for this course, we're going to pretend that that's a legitimate objective. Okay, so let's suppose I know something and I want to convince you, but I don't want to tell you what I know. I want to convince. So, for example, there is a graph, or there is a formula, and I tell you that it has a satisfying truth assignment. It's a positive instance of SAT, but I don't want to give you that instance. Now, why would anyone, I mean, apart from like strict, like just it's perverse and kind of fun, like do not do this on your next homework assignment. Do not try to do a zero knowledge proof of knowledge to convince the marker that you know what the answer is, but you don't want to write the answer. Don't do that. That's not cool. It's kind of cool, but don't do it anyway. But you can actually use this in crypto, right? Because suppose that what I'm going to do, I have something. I have this formula. Okay. Suppose that I built this formula ography or coin? What? I don't understand what ography question mark means. Okay, cryptography. Yes, cryptography. So I'm going to. So one of the things you sometimes want to do in cryptography is prove to somebody that you are who you say you are. Right? A proof of identity. Now, there are various attacks against this, like man-in-the-middle, blah, blah. But let's suppose that I have built this formula in such a way that I know a satisfying truth assignment, and it'll be hard for somebody. I believe that P is not equal to NP, and it's going to be hard for somebody else to find a satisfying truth assignment for this. It'll take them more than polynomial time. So I have this satisfying truth assignment, and I have this formula. I publish the formula. That's public, right? So I stick it on my website and I say, I, Travis, know the answer, know a satisfying truth assignment for this formula. And I believe that other people in a reasonable amount of time are not going to be able to find this satisfying truth assignment. So if I meet you on the street and you want to know if we're at a fancy dress party or something and I'm in costume and you want to know that it's me, ask me to give you, to show you that I know the satisfying truth assignment. Now, okay, so we're at a Halloween party or something where I'm in costume and you say, you know, are you Travis? Are you my professor? And I say, yes, I am Travis. And you say, oh, well, I would like to buy my professor a drink, but I don't really believe you're my professor. And I said, well, I don't want to take the mask off. It takes so long to put this costume back on. But just believe me, I'm Travis. This has never actually happened, by the way. So just believe me. You say, I don't believe you. I think you're somebody else trying to just scam a free drink. And I say, well, I can prove to you I'm Travis because I know the satisfying truth assignment. And you say, oh, that's great. Give me the satisfying truth assignment. I'll check to see that it actually satisfies the formula. I say, oh, but if I give you the truth assignment, then you're going to know it. And then you're going to be able to go around this party and find my students and get free drinks that are actually intended for me. So this, instead, to prove to you that I am Travis, I want to show you that I have a satisfying truth assignment, but I don't want to tell you what it is. So this is like when your computer connects to the bank, you want to prove to the bank that you are who you say you are, but, well, okay, I guess you trust your bank, but maybe something, you know, you want to be able to prove you are who you say you are, but you don't completely trust the other party. So you don't want to give them sort of your private key, if you know crypto. Okay, so how do I prove to you that I know something without telling you what I know? Okay, so do people know Sudoku? This was popular. I know Sudoku was super popular a few years ago. And so, yes, some people, yes, okay, it's still popular. I was gonna, actually there is, I didn't do a proof that Minesweeper is NP complete because I'm not sure people these days know Minesweeper. Like it was popular 20 years ago. Okay, so you know Sudoku. Sudoku is 9 by 9. Who's Stanley? Sudoku is 9 by 9. So that's actually, 9 is a constant. So I could just burn through, like, what are all the possible ways to fill? Well, there are 10 numbers, right? No, wait, that is not 9 numbers. When ignoring zeros. Okay, so there are 9 digits. So how many possible solutions for a 9 by 9 Sudoku are there? At most 9 to the 81, which is a big number, but it's still a constant. I can't say something about the complexity of normal Sudoku, which is 9 by 9. I can say something about the complexity of n by n Sudoku. So let's suppose n is a square. So 100 by 100 Sudoku, right? Then you're going to have 100 rows, 100 columns, and you're going to have, each row is going to, you're going to have like blocks of 10, right? So 10 by 10 blocks, and you're going to have 10 blocks across and 10 blocks down. And in each of these blocks, you can put the numbers between 1 and 100. So n is 100. It'll be n by n, and n is a square. So you can have these squares which have 1 to n, and you line it. And it's like, okay, so you could generalize Sudoku. Generalized Sudoku is NP complete. You can actually, if you could solve generalized Sudoku, n by n Sudoku, you could solve SAT. Okay. Somebody has done a reduction from some NP complete problem, I don't know which one, to Sudoku. So I'm going to show you how to do, and this is an easy proof, right? I've actually done this to my niece years ago, when she was like very small. Suppose that I want to prove to you that I know, you come to me with a Sudoku problem, puzzle, and you say, I don't think this has a solution. This is too hard. I've been trying for ages. I say, no, it does. I know it. And you say, I don't believe you know it. So then what I can do, now this, the first I'm going to tell you is called a physical zero knowledge, proof of knowledge. I take cards. So I take n by n squared cards. So for a normal Sudoku, I take 81 cards, okay? And on the backs, I write the positions, right? So I can have like a card, and I write 3, 1, meaning that it's in row 3, column 1, okay? So I'm going to have everything from some card, which is labeled 1, 1, down to some card, which is labeled 9, 9. Okay, so on the backs, I write the positions. On the fronts, I write the number that's in that cell in the solution. Now, we lay the cards out. So there's you on that side of the table and me on this side of the table. We lay the cards out face down so that you can see that they're in the correct positions. And then I say, okay, the numbers which are showing, the numbers that are filled in the instance of Sudoku, turn those cards face up, right? So you can see that they are the right numbers, okay? And then turn them back face down, okay? Now, take each column and gather the column. So you gather the column into a little deck of cards. Okay. So now you have 9 decks of cards. Shuffle each deck. And now look at them, not looking at the backs, now looking at the fronts. Just check that each deck contains the numbers 1 to 9. What does this tell you? Okay, when they were face down, you checked that, you know, the things, the numbers that we're showing were in the right place. You've checked. You've checked that I'm actually solving the instance of Sudoku that I claim I'm solving. Now, when you gather the columns into the decks, you shuffle the decks. Yes, so you have 9 decks. So you check, and each deck, you're not looking at the backs, only looking at the fronts. You check that it's the numbers 1 to 9. What does this tell you? It tells you that I found a way to fill in the numbers for this instance of Sudoku such that each column contains the numbers 1 to 9. Okay, now pile the cards up again, and now lay them out again, pile them up, lay them out again, and now gather every column into its own deck, and check that, shuffle the deck, and check that first 4 columns, now rows. Gather every row into its own deck, shuffle the deck, and check that it contains the numbers between 1 and 9. Okay, what does this tell you? If at some point I'd put 2 copies of the same number in some row, you're going to find that. When you gather that row into the deck, you're going to shuffle it, and you're going to look and say, what are you talking about? This deck, it has 2 2s and no 5s. You lied. It's not a valid Sudoku instance. But, you know, you gather them up, you shuffle it, you check each deck, and you say, okay, fine. I believe you that every row contains the numbers 1 to 9. And now you pile them all up, and then you lay them out again, and now you gather every square, 3 by 3 or n by n or whatever, square into its own deck. You shuffle the deck, and then you check it contains the numbers between 1 and 9. Okay. And then you say, okay, so now I believe you that every square contains the numbers 1 to 9. That means I've proven to you that I have the solution, right? Because a valid solution is just one where the numbers that are showing match. So I'm solving the instance you give me. And all the columns contain the numbers 1 to 9, all the rows contain the numbers 1 to 9, and all the squares contain the numbers 1 to 9. So you could actually do this. You could actually do this with, say, your niece, if you have a niece, nephew, friend, whatever. So what have I told you? Okay. Well, since you gather a column and then you shuffle it, all you learn is that because you've shuffled it, all you learn is that that column contains the numbers 1 to 9. But you don't learn anything, assuming you shuffle it decently, you don't learn anything about how they're ordered. So you learn nothing about the solution apart from the fact that I have a solution. You learn that, yes, the numbers that are showing these are actually that my solution actually has those numbers in the correct positions, and that my solution, all the columns, all the rows, and all the squares contain the numbers 1 to 9, and you learn nothing else because you shuffle it, right? Do people understand this? Okay, 1, 2, 3. Okay, so given that I have 13 students, that's like, you know, a quarter, sort of. Okay, so this is actually, I can prove to you that I have a solution for an instance of Sudoku. Now you could actually explain this to sort of people like your niece, your nephew, your grandmother, whatever, your friend should believe you that you have a solution. And this generalizes to n by n. So in fact, if you have a formula, if somebody if there's a formula and you have a satisfying truth assignment and somebody doubts that there is a satisfying truth assignment, what you can do is look up the paper that has these reduction, the proof that Sudoku is NP complete, take the formula, turn it into an instance of Sudoku. This will map your satisfying truth assignment will map to a solution of that Sudoku instance. And then you prove to them that you can answer the Sudoku instance. And so you have proven to them that, that you have a satisfying truth assignment. Now, this, like I said, this is a physical proof, right? This only works if sort of you're across the table and I'm across the table and we have some cards and I trust you when you gather the column into a deck and you shuffle it, that you don't just be like, yeah, I think I'm going to find out what these are. So, and you turn them over and you don't shuffle them and you just look at them. I have to sort of trust you about that. Now, let's talk about a way where I don't have to trust. So I could, for example, at the Halloween party, I could prove to you my identity by turning the formula into a Sudoku instance and proving to you that I know a solution to the Sudoku instance. So let's talk about how would I do this if we're communicating over a channel and we can't like, write numbers on cards and, I tell you, okay, now here they are, now shuffle these, blah, blah, blah. Let's do this with some crypto. So the first problem, the classic zero knowledge, proof of knowledge problem is our old friend, three colorability. Woo! And this is also where in the Sudoku stuff, the physical proof, you actually know for sure that I have a solution. In this case, you're only going to be as sure as you want, but not quite 100%. Okay, so how is this going to work? Are people following this, like, interested? Anyway, okay, so let's suppose we have a graph. Okay, this graph. And is this three colorable? Okay, so let's just put some, let's see if we can come up with a three coloring. Okay, so this is, let's say, red. This is green, blue. This has to be red, but this can be blue. So this can be red. This can be red or blue. This can be blue. This can be red. Right. So let's suppose I put. Oh, I forgot to start the timer again. I can do. I have to do like 16 minutes. Okay, so I have put all the work into this. Maybe I built the instance in such a way. I mean, it's possible to generate instances, assuming P is not equal. And okay, there's been work on sort of generating hard instances, right? Because there's a lot of trickiness here. Because, for example, maybe P is not equal to NP, but it's really hard to find a hard instance, right? Like there are. This is why one reason why we can solve a lot of problems in practice, because hard instances are rare and sort of weird, and you have to build them you have to build these pathological hard instances in a special way. So, but the hard instances are useful because it's no good if I'm at the costume party and I have an instance of Sudoku and somebody says, oh, well, okay. And you just look at it, you can figure it out. Then you can go around pretending to be me. It's bad. It's like, we actually use hard instances in crypto, and you want to be able to generate instances that really are hard in order to keep your bank account safe. Okay, so let's suppose I put all this work into building this instance. Is there an impossible problem? An impossible one. There are problems like the halting problem, but no, everything in NP we can do. But I'm not sure. Okay, what did I do with my pen? Oh, there. So all of this stuff I'm showing you is assuming that if P is equal to NP, almost all crypto breaks. I mean, one-time pads still work. I'm not going to tell you what a one-time pad is. Okay, it's basically you just like flip a coin, you generate a string of numbers, and then you have somebody actually carry a suitcase with that string of bits that you've generated with a coin over to some other party. And if you want to send a message, you use that you write your message and then you XOR it with this randomly chosen binary string. And then you send it, and to anybody else, it looks random. It is random because each bit is 50% 0, 1 because it's been XORed with the random coin, with the flip of a fair coin, except to the person who has the other copy, and so they can decrypt it. This actually is for communications between the US and the Soviet Union back in the days of the Soviet Union. They used one-time pads. The thing is, it's called one-time pad because you can only use it once to be absolutely secure. Because otherwise, if you keep using it, then if somebody knows one of the messages you sent, they can work out your one-time pad and then they can read all of them. Okay. So there's also, I think if P is equal to NP, some quantum crypto still works. But I stay away from quantum stuff. If you want to know about quantum stuff, you have to ask Sarah. She loves that and is good at it, knows about it. I don't. Okay, zero knowledge. So what I'm gonna, I've worked out this solution. And so to prove to you that I know a 3 coloring of this graph, but I don't want to tell you the 3 coloring. So what I'm gonna do is I'm going to choose. So actually, I'm not going to call this red. I'm going to call this 1, 2. This is the bad black marker, or is this the good black marker and it's failing? Yeah, this is. I'm not going to call this red. I'm going to call this 1, 2. No, this is 1, 1. This is 2. This is green is 3. This is 2. And this is 1. So now what I'm going to do is I take this graph. So we agree on the graph. We looked at the graph. I'm going to take, I'm going to choose some random. I'm going to decide that 1 is red, and 2 is blue, and 3 is green. Okay? Okay, so I'm going to choose some bijection between the numbers 1 to 3 and the colors red, blue, and green. I'm going to color the graph, and then I'm going to encrypt each vertex color separately. I don't encrypt the whole graph. I encrypt each vertex color separately. and I send you the encrypted colors. Okay, so now you have each vertex, you have the encrypted colors. So now what you do is you ask me, okay, this edge. So if I don't have a solution, then I must have colored for one of the edges. If I don't have a 3 coloring, then I have to have colored for some, at least one edge. That edge has 2 endpoints the same color. So you pick an edge at random. Right? So let's say there are m edges. So you pick an edge at random and you say, okay, this edge. Okay, this edge. Then I send you the keys to this vertex and this vertex, their colors. And you decrypt them and you say, oh, this is green and this is red. They're not equal. Okay. So you say, okay, I have some evidence that you're not lying, that you actually have a 3 color. Okay. So, but the thing is, you don't have very much evidence. Like, why would you believe me? You've only checked one edge. Now, what you could do, you could ask me for more keys, but then I would be leaking information. Because if you check this edge, and then you check this edge, you find out that this is the same color as this. You find out something about my solution. So I don't want to do that. Instead, what I do, so you've checked one edge, so the probability, one check, probability of catching me cheating is 1 over m. Okay. So if I've lied, the probability that you choose the edge I had to color both endpoints the same is 1 over m. That's pretty weak, right? Like if the graph has 10,000 edges, you probably aren't going to catch me. I can get away with 1 check. So now what we do, we repeat this, but I forget my original assignments, and I generate a new assignment of 1, 2, 3 to red, blue, green. Maybe and I do this randomly. Right? So maybe it comes out to be the same, or maybe it comes out to be red, green, blue. Okay. And now I recolor the graph. And I encrypt every vertex's cover. And I send it to you. And now you randomly pick an edge. And you could pick the same edge, because maybe I'm being sneaky and say, oh, well, you check this edge. I can afford to make this red and this red now. And I can cheat. So you just pick the edge randomly. And then you pick the edge. I send you the keys. You unlock the vertices. And you say, okay, I pick this edge, this is blue, this is now green, and this is still red. So you check again. Now, what's the probability after this second check that I could get away with cheating? Well, the probability that you catch me on the first check is 1 over m. The probability that you catch me on the second check is 1 over m. So the probability that I get away that I'm cheating and I get away with it is catching me cheating. So probability I get away with cheating after k checks is 1 minus 1 over m to the k. So yes, for 1 and 2 checks, I'd probably get away with it. But if there are 1,000 edges and you do this 1,000 times, okay, there are 10,000 edges and you do this 10,000 times, 100,000, then the probability, you can drive the probability down exponentially small. So you're never exactly sure that I'm not cheating you. And yeah, I mean, this, but how much time are we taking? Well, it's still a polynomial, right? So it's polynomial. If you want to be more and more sure, then I can use more and more checks, but I only need a logarithmic number of checks to drive it. Log in 1 over the probability that you want to have the chance that they get away with cheating. Okay, so so this is how you do zero knowledge when you're not in the same room and you can't use cards. Okay, and 3 colorability is NP complete. So any problem in NP, if I say I have a solution to the problem and you say, oh, I don't believe you, then we can reduce it to 3 colorability, and then we can do this protocol where, you know, at each step I have to randomly recolor and say, now oh yeah, I forgot the key thing. Why is it a zero knowledge proof? Why am I not leaking any information? And this is the key part, why I randomly, after every step, okay, so this is, I've been trying to avoid, it'll be in the lecture notes. NP complete means it's NP hard means if you could solve it in polynomial time, then P would equal NP. NP complete means it's NP hard and it's in NP. So problems that we can solve in polynomial time are in P and therefore in NP. The halting problem is NP hard. If we could solve the halting problem, then P would equal NP. This is not true. So I mean, but there are problems which are harder than that are outside NP, isn't it? So this is the probability. Sorry, I'm still short on sleep. Trust me, you can see these big black bags under my eyes. If the probability I get caught at each check is 1 over m, then the probability I don't get caught is minus 1 over m. And so the probability that I don't get caught in k checks is 1 minus 1 over m to the k, isn't it? Yes, the probability I get away with cheating after k checks. The probability after in 1 check, the probability I get away with that I get caught is 1 over m. So the probability, so this is something less than 1, and taking it to the k. So if I wanted to, if you want to say I want the probability that Travis gets caught, if he's cheating, that Travis gets caught is 99%, then we can work out how many trials it's going to take, and it's going to take basically something like log, and the base of the log is going to have to do with m, and then we log the 99%. Okay, something like that. I didn't work that out in advance. So, but why am I not leaking any information? Because in 1 trial, all you find out is that this is green and this is red. And then if you check again, you find out that this is red, and in the next trial, this is red and this is blue. And then in the 3rd trial, you find out that this is green and this is blue. And then you find out there's no way to put these pieces of information together, because in each trial, you could actually generate this yourself, right? You could just flip a coin. Like if at the end of all these trials, at each trial there's been different colors, there's no way to combine that, because if this is green and this is blue in this trial, and this is red and this is blue in the next trial, how do you put them together? So in fact, you could just say, okay, I believe if Travis gets away with this, you could just yourself just pick colors randomly, pick pairs of colors that are not equal, and that gives you the same information. You could generate a transcript of our conversation. You don't need me. So if you could do this yourself, then I'm not leaking any information, right? That bit gets a bit fuzzy, but it's easier with the Sudoku. That's why I started with that one. Actually, okay. So now I'm gonna finish it. So this is something that you could actually do the Sudoku with a friend. And this is actually used. So in crypto and complexity, like modern crypto is built on top of complexity theory. So, and modern crypto is actually used in really practical stuff. So this is sort of an answer to these people who say, why do we have to learn this? This is just theorists being like weird. Like, why are we studying all this stuff we can't do? Now, so what we know and want to prove we know is reduced to 3. And then, okay, so yeah, if for example we have this formula, and I say I have a satisfying truth assignment, and you doubt me, then what I could do is we've seen the reduction of sat to 3 of 3 sat. So we used Satan's transform to turn it into a 3 CNF. And then we've seen the reduction of 3 CNF to 3 colorability. So we take the formula, we turn it into a graph, such that this graph now, our reductions actually, if you have a solution to this, it maps to a solution to this. So if I had a satisfying truth assignment to the formula, I have 3 coloring, and now we can do this protocol, and I show you that I know a 3 coloring, and since we both agree that the reduction is valid, you know that I have a satisfying truth assignment. So that's why this is one use where it's actually cool that all these things are equivalent, because that way I only have to come up with a protocol for 3 colorability. I'm just going to start at least with this point. Now, we're actually running out of time. I didn't think this was going to take so long, but the other thing I want to show you is something called it's called a fine grain reduction. And I start the counter again. Although actually, yeah, when we get to 12:55, it'll be 25 minutes. I'm just going to check. Okay, so one of the hot topics in complexity theory are these things called fine grain reductions. And what this means is that you can show you things we assume are hard, really, really hard. You can show that if they are really, really hard, then you can't do something in subquadratic time. So the big one, the really famous one, is edit distance. So strong. So there's something called the strong exponential time hypothesis. I think this is hyphenated, or at least it should be. Maybe it isn't usually. So this is known to its friends as SAT. Okay. So what does the strong exponential time hypothesis say? We cannot solve in 2 to the, I think I'm getting this right. I think it says minus epsilon time for epsilon, constant epsilon, positive constant epsilon. And this, of course, is in the worst case. Where n is the number of variables. Okay. So obviously you can solve SAT in something like 2 to the n time, where n is the number of variables, because you just check every possible truth assignment. There are, how many of them are there? There are 2 to the n. Each variable is either true or false. Okay, but SAT says you can't do this in 2 to the n minus epsilon. Okay. So is that clear? So that's saying that SAT is really, really hard. There's nothing that really beats the naive approach of just try everything. Or not by, I mean, yeah, maybe you can shave something like a log or a polylog factor off. So this is talking about SAT and stuff that takes exponential time, well, super polynomial time. This is saying that it takes exponential time. Okay. So people showed that if SAT is true, I'm not sure people actually call it SAT. I've heard it said, but it's definitely written SAT, but maybe they say SETH. SET is easier. So, okay, if SET is true, people have shown that you can't do, okay, so this was a theorem by Aboud and Indik, I think. So there are a bunch of people on there, a bunch of people working on this, like Brinkman and Vasilevska Williams, and so, but I think it was Amir Aboud and no, maybe I'm getting confused. I have to look up who actually. I think it was Indik and something. But they showed that, so theorem, if SET is true, then we can't solve edit distance. In n to the 2 minus epsilon time. Right? So you can't, so this is called strongly subquadratic. So it says that you can shave off like log factors, polylog factors, but you can't do, in the worst case, you can't solve edit distance. The edit distance we know, how to solve in quadratic time because I forgot to reset this, but it doesn't matter. We saw how to solve it in quadratic time. Now there are we also saw banded dynamic programming, which actually in practice does better than quadratic time, because we usually we're computing the edit distance. But in the worst case, for years and years, people didn't find anything subquadratic. And this sort of explains, well, we're unlikely to, if Seth is true, then there isn't a subquadratic algorithm. Right? So Seth is a stronger hypothesis than just P is not equal to NP. P could be different than NP, but you could still have something that was like 1.5 to the N or something like that. So Seth is saying P is not equal to NP, and SAT is pretty much as hard as we think it is. There is nothing much better at SAT. If Seth is true, then you can't get a much better algorithm for edit distance that works in the worst case. Okay? And I'm going to prove this. I'm not going to exactly prove this to you. I'm going to show you one of these reductions from something that ties together a polynomial time problem and an exponential time. Something that we know how to do in polynomial time to something that we don't know how to do in polynomial time. Okay? Questions? So this is kind of cool because you get lower bounds for problems that we can do in polynomial time, but we would like to do faster. And we prove them on the basis of things we believe about problems we can't do in polynomial time, or at least we think we can't, assuming P is not equal to NP. Okay. And I'm going to try to do this in 17 minutes. Do I still have students? Oh, I've lost a couple of people. Okay, so I'm not going to show you the reduction from SAT to edit distance because I don't know it offhand. I should have looked it up last night, but I was trying to write the lecture notes. So some of the lecture notes are for I'm catching up very slowly. Okay, so what I'm going to reduce to is, let me see if I'm going to reduce SAT maybe I'm going to reduce 3 SAT. Yeah, I think I'm going to reduce 3 SAT to a problem called orthogonal vectors. Okay. So orthogonal vectors, you're given for orthogonal vectors, so we're given 2 sets of vectors. Say they're d-dimensional, and 2 sets A and B of d-dimensional vectors. D is going to be pretty small. Okay, and we're going to assume binary. Okay, so for example, maybe you get 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1. And you get 1, 0, 0, 1, 0, 1, 1, 1, 1, and 0, 0, 0, 0, 1. Right. Okay. So I'm not saying that they have to be distinct. Okay. So this is A and this is B. Now we can do this in assuming D is not very big. Let's assume that D is like polylogarithmic in the number of vectors in these 2 sets. Then the question is there a vector in A and a vector in B that are orthogonal? That is, their dot product is 0. And here it is. For example, 0, 1, 0 and 1, 0, 0. If you take the dot product of those two vectors, it's 0. Those two vectors are orthogonal. Clear? Anybody? Still there? Okay, how long would it take us to do this? Assuming, ignore D for the moment, like it's small, it's polylogarithmic. All right, roughly, how long would this take? Could you write an algorithm that does this in polynomial time? So let's say that there's n vectors in A, I'm not going to say n, I'm going to say m vectors in A and m vectors in B. How long is this? How long would it take? No, just to tell me, can you pick a vector in A and a vector in B such that those two are a vector V sub A in A and a vector V sub B in B such that V sub A dot V sub B equals 0. So they're orthogonal. Just to find, yes, right? You check every vector in A and every vector in B, and like you do this pairwise thing. How long does the dot product take? It takes you like time D, but I told you to ignore D because D is small. So orthogonal vectors is basically quadratic time. Right? You can do n times n. Easy. Okay. So how can I reduce 3-sat to orthogonal vectors? 3-sat is hard, and orthogonal vectors is easy. Well, the key thing is, this is not going to, so I started teaching this because in 2019, somebody in the class said, do reductions always have to take polynomial time? And I said, no. All the reductions you normally see in third year take polynomial time. But technically, this works because the reduction takes exponential time. Okay. Can we optimize that? That's the key thing. That's what we're going to talk about. We're going to show that if Seth is true, you can't do better than quadratic time for orthogonal vectors. Right? It's easy. Somebody just came up with the algorithm for solving orthogonal vectors in roughly quadratic time. We're going to see that if SAT is as hard as we think it is, then that's about the best you can do. That's kind of cool. It ties together like SAT, which is like something far away and really hard that you don't want to work on, and orthogonal vectors, which is something easy and which you can do in polynomial time. Okay, so remember, we cannot solve SAT. We're saying that SAT you can't do it in 2 to the n minus epsilon. I have to remember, I hope I get this right, and I hope I can do this in 10 minutes. It's not actually a hard proof. I'm just going to make sure that this thing is recording again. Okay, so maybe I should tell people who are confused about this NP stuff not to watch this lecture, because it's just seeing an exponential time reduction is just gonna confuse. But if you're understanding this, given a 3-sat formula F, with n variables, we split, and let's say n is even, okay? Say n is even. We split the variables into two groups. Right? With n over two variables each. Okay, so we're going to call these variables, we're going to call these group things group X and two groups X and Y. Okay, so they have n over two variables for each of them. Now, what we're going to do is take the variables in group X and consider all the possible truth assignments to those n over two variables. All of them. Okay. So how many are there? 2 to the n over 2. Okay. And the same thing for y. All the truth assignments to variables in y. Now, what we're going to do is for each of those truth assignments, we're going to write a vector. Okay. For each of these truths. So now this is the sneaky bit. For each clause, so for a truth assignment, tau to variables in X. Compute which of the clauses are made true by tau. We write a vector v sub tau saying which of the clauses is made true by tau. Now, some of the clauses tau will not satisfy, right? Because it only tau is only talking about half the variables. So it satisfies a clause if, for example, that clause contains x10 and tau x. Oh, x is back here. It contains variable z10 and tau x contains z10 and tau says it's true. Then tau satisfies that clause and we write that in the vector, okay? And or if there are 2 to the n over 2 taus for x and 2 to the n over 2 taus for the other n over 2 variables, right? So the sneaky thing is, when we write these vectors, when we write the vector v tau for tau, if tau satisfies the ith clause, makes the ith clause true, regardless of what the truth assignment to y, then we don't write a 1, right? You would automatically think 0 is false and 1 is true. That's not what we're going to do now. We write, if it makes it true, we write a 0. And if it makes it false, or if it makes it false, if it doesn't satisfy it, that is, maybe it assigns, maybe there's a variable in there which is not in X. So, you know, it doesn't make the variable. So if it's like Z10 or Z15 or not Z27, and Z10 and Z15 are in X, but tau makes these both false, and Z27 is in Y, then this tau doesn't satisfy this. Maybe you could still set Z27 to satisfy it, but tau by itself is not enough. Now, if tau says Z10 is true, then great, tau satisfies this and you write a 0. If tau doesn't satisfy this by itself, you write a 1. Okay? So, I should have come up, in the lecture notes, I'm actually going to use this as, I'm going to come up with I'm actually going to write the SAT formula from, the 3 SAT formula from the other day. So, I have 3 minutes, so I'm just going to say this. Okay, so you end up with, well, no, okay, I'm not just going to say this. I'm going to erase this. So we get 2 sets of 2 to the n over 2 vectors of length k. This is number of clauses. But how big is k? How big can k be? Well, it's not that big because there are only n variables. So there are 2n, not 2 to the n, 2n literals. And then you can, for each clause, you choose 3 things. You choose 3 literals, right? So it's like, k can be at most 2n, choose 3, which is like 2n cubed. So it's something like n cubed. So it's polynomial in n, whereas these sets are exponential in n. So the dimension of the vectors is really small. We're just going to ignore that, right? So suppose you have these 2 sets of vectors. Suppose that 2 of them are orthogonal. I have like 1 minute. Suppose that 2 of them are orthogonal. Now, what does that mean? That means that for every component, either for every I, so remember the i's, the components of the vectors are the clauses. Either the ith component is 0 in the vector from A, which means that the truth assignment to X satisfies that clause, or it's 0 in the vector from B, which means the truth assignment to Y makes this 0. So how much time does it take us to build these 2 sets of vectors? I'm over time, sorry. Well, this is only going to take, to generate these vectors, it's going to take about 2 to the n over 2 time, right, times 2. And then, so if we can figure out, if we could say, are there any of these vectors that that are orthogonal, then there would be a satisfying truth assignment, because we would say, oh, well, then we take the tau to X that gives us this vector from A, and we take the whatever tau, the truth assignment to Y that gives us this vector, and then when you put them together, every clause is satisfied, because either it's 0 in the vector from A, every component, which is a clause, is either 0 in the vector from A or 0 in the vector from B, or both. if neither truth assignment satisfies a clause, then it's 1 in, then we put a 1 for that clause in both vectors, and the dot product of 1 and the product of 1 and 1 is a 1. So the total dot product is not 0. The two vectors are not orthogonal. Right? So we can take this formula of set and we can turn it into these two sets in time, like 2 to the n over 2, or roughly. We can turn it into these two sets of vectors such that if two of those vectors are orthogonal, then there is a satisfying truth assignment. Okay, so if we could do this so this, we're going to say this is not 2 to the n minus 2 anymore. We're just going to call this m. If we could do this in better than m squared time, say we could do this in m to the 2 minus epsilon, then what would that mean? We could solve set in, well, now we're going to call this again, we're going to change m back to 2 to the n over 2 minus to the 2 minus epsilon. And what is this? This is 2 to the n, and this is like minus 2 times epsilon times 2, this times something, yeah, okay. So I'm actually getting some minus epsilon times n over 2. Well, this is, right, this is 2 minus epsilon, 2 n. I'm over time. Look, I correct. But you see, do you see how this goes, my 10 remaining students? You can work this out. You could, if you do this, maybe I stated slightly. If you do this, you say, okay, if we could get a subquadratic algorithm for set, for orthogonal vectors, it would mean that by turning set into an instance of orthogonal vectors, we could solve set in better than 2 to the n, better than 2 to the n, 2 to the n time. Now, the key thing is this reduction is not a polynomial time reduction, because how long we're taking a formula that's like of size n, and we're turning it into two things of size 2 to the n over 2. It's an exponential time reduction. But this ties together, this says if SAT is as hard as we think it is, then orthogonal vectors you can't do in subquadratic time. And that nobody was really like, that's weird. And the small camera has stopped recording, so you can, okay. So that was a bit confused, but you don't have to know this. This will not be on the midterm because it's like not normally included in third-year algorithms courses. I just wanted you to see that that P versus NP isn't just sort of this thing for like nerdy complexity theorists. That this actually, I mean, okay, this is still sort of nerdy complexity theory, but it has to do with problems that people actually work on and think they've solved and say, I can do this in quadratic time, but why can't I do this in subquadratic time? Why can't we find an n log n algorithm for orthogonal vectors? Because if you could, then you could do SAT faster. Okay. Thank you for listening, even though you won't be tested on this stuff. So zero knowledge in orthogonal vectors, and I managed to go over time even on this stuff. But you see, it's not that hard. Wait, what is this? I just see a bunch of lines. Okay. People can disappear. It's now past 1 o'clock. It seems like a semi-nice day outside. I will try to get the lecture notes up. I don't know which I should try, like writing the midterm or writing the solution or writing the lecture notes. Probably writing the lecture notes. Good luck on the midterm and see you in a couple of weeks. Cheers. Stop the recording.